Okay, so shall we get started? Everyone, welcome to lecture 4 on a nice sunny day. It's unusually sunny for October, right? Okay. So hopefully this is something you're very familiar with. So when is quiz section this week? It will be Wednesday, 5 and 6. Wednesday. Okay, so we'll have quiz section Wednesday, 5 and 6. Quiz section will have information that's going to help you with your assignment. And office hours is something that you can ask any questions, right? So it's open-ended. Okay, so I have, after class today, usually I'll stay back for some time. If you have questions, you can talk. So someone asked about late days, late submission policy. So we've done this before. So I was just thinking about it, and maybe we can have 5 late days for the whole quarter. So you can use it in one assignment or spread across assignment or not use it at all. So whichever is your option, and you will not incur a penalty. But if you exceed 5 late days, then it doesn't matter. Even if you're a day late, you'll have 10% penalty on the grade. That's sound good. So use your late days wisely. Like you really have a busy week, okay, then use the late days. If you can do it, then just do it, right? Don't delay. So today we'll continue with unsupervised learning and look into clustering, kMeans, kMeans++, and tSNE to help us understand image visualization better and image clustering. Okay, so yeah, big picture, we're here. We spoke about this last time as well. And within this, we're covering data visualization today again, but we're also covering clustering. So we're covering both today. We spoke about the clustering problem last time, example of flowers. Cluster the flowers into different clusters. So typically you need to know what K is. K is the number of clusters, right? And we also spoke about clustering versus classification. You have a label in the case of classification, and if it's clustering, you just have Xi, so there's no Y. So there's different examples. You can cluster digits, right? And I think we'll also look at a couple more examples. You can cluster news. You have different news articles, and you want to cluster them into like sports, world news, politics, other kinds of news. So you can do clustering for anything, basically. Although we'll be talking about images in this course, you can apply it anywhere. So kMeans is going to be the main algorithm that we will use to do clustering. How many of us have heard of kMeans before? 1, 2, 3, 4, 5. So we'll talk about kMeans, what does it do, how does it work, and we'll also look at its disadvantages, and we'll look at how we can address that as well. So this is an example of data points. Data points not clustered. So this is 2-dimensional, right? 2 dimensions. So data points in 2 dimensions, and they're not clustered. And here you can see they are clustered with k equals 3. So this is like very good clustering, perfect clustering. So we'll talk about perfect clustering, imperfect clustering, and what that means. So if you were to look at news, for example, news as an example, and let's say you want to come up with 4 clusters, like maybe, people have different preferences for what news they want to hear or what news they want to watch. And maybe there are different kinds of topics in the news, right? So sports, world news, entertainment, and science. So in clustering, you don't know that these topics exist, right? But But with news, you do know like, okay, there's probably like 4, 5, 6 different clusters you can have. So you can pick your K based on that and do the clustering. And hopefully these clusters are able to capture different kinds of news, right? So that's clustering for news. Obviously, you can do it in a supervised way. So if it's supervised learning, we'll use something called multi-class classification, which we'll cover in the next lecture or the lecture after that. Here, obviously, you have a label, and you want to predict the label. But if the labels are not known, you would do clustering. So let's look at a little bit more on clustering. In many real-world contexts, there aren't clearly defined labels. Like no one's going to tell you this is a sports news, this is entertainment, or this is a science news article. No one's going to tell you that. You may have to figure it out on your own. Like someone writes an article, and then maybe they have some keywords, maybe they don't have some keywords. But you may be a news aggregator site, and you want to aggregate news from different places, but you want to still cluster them. So it's easy for your users to actually go and browse those categories and then figure out what articles they would like to see and what articles they don't want to see. So in many real world contexts, maybe I'll just stand this way. Okay. This is easier. So in many real world contexts, the labels are not clearly defined. So we won't be able to do classification because you need labels for classification, right? So clustering is a process of automatically trying to, put things together into different clusters. So maybe here we'll say, okay, this is one cluster, this is the second cluster, this is the third cluster. So these are, so these Z ones are basically so X, let's look at the notation. So X refers to inputs, is input 1, input 2, and so on, right? And what is Z? What is Z here? So what's happening on the right? You're taking each point and assigning it to a cluster, right? So it's not just that I'm drawing these circles around it, I'm also saying you belong to this cluster, right? So this would be like cluster 1, this is cluster, this is cluster 1, this is cluster 2, and then this is cluster 3. So the Z is going to tell you, is it 1, 2, or 3 for every single data point, right? So you'll basically say, okay, here, Z10 is equal to 1, right? And here, Z20 equals 2. So everything here is going to be having Z20 equals 2. And everything here is going to have Z whatever equals 3. So that's called cluster assignment, right? Let's call it cluster. So any clustering algorithm is going to have cluster assignment. It's going to have number of clusters, and it's going to take each point and say, which cluster do you belong to? This one, or this one, right? So that's what Z represents. A little bit more about clusters. How do you define a cluster? Well, it has a center, right? So for instance, here you can see, so this is a center, right? This is a center, and so on, right? So every cluster has a center that kind of defines the central point of that cluster. And a cluster also has a spread or a shape, right? Typically, you assume if you don't have any information, you say a cluster is circular, but it doesn't have to be circular. It can be spiral, it can be elongated, it can have different kinds of shapes. So in this example, so here you can say maybe this is a circular cluster, right? But if you look at this one, this looks more like a elliptical cluster, right? It has that kind of a shape. So it's not necessarily circular as the red one. Also, there is spread. Spread tells you how spread out the cluster is. So which one is more spread out, the red one or the green one? Green, right? Spread is you just look at how far the points are in the cluster. So obviously the green one is more spread out. A cluster could be more dense. It could have a lot of points and still not be spread out, right? It looks like red one has a lot of points as well as compared to green, but green one is more spread out. So the number of points doesn't necessarily tell you about spread. It's more about how much distance is there between different points in the cluster. Yeah, and as we discussed, the clustering is basically a process of taking an xi and saying assign a zi to it, right? And zi will be in between 1 and k. So it can be any value between 1 and k, where k is the number of clusters. So we'll talk about an algorithm that helps us with clustering. It's called kMeans, and it's usually based on identifying the closest centroid to a point. So here, with this figure, we already see a red center, a green center, and a blue center, right? So the centroids are obvious. Now you say assign a point to a cluster, you'll say, oh, that's easy, right? Like if I want to assign, let's take an example. So let's say I have this point. Which cluster am I going to assign to? Well, it's easy. This centroid is closest, so I'm going to assign it here. I will not assign it to the blue one. I will not assign it to the red one because they are far away. But that's because you already identified the centroids. You already said the centroids are in a good place. So once you know the centroids are in a good place, it's very easy to assign the centroid, points to the centroid. But the question is, how do you even figure out what are the right centroids for these clusters? So now we've broken down the problem into two. One is identify the right centroids for each cluster, and then assign each point to the closest centroid, which is easy. So that is what the kMeans algorithm is all about. And we'll talk about that in a bit. So kMeans is identify centroids, identify good centroids. That's one. And then second is assignment. So you identify good centroids in an iterative process, and then also assign every single point to one of these clusters. It's the same thing. Assigning a point to a cluster is the same as assigning a point to a centroid, because you're picking the centroid that's closest to that. Okay, so since we've been talking about a centroid, let's actually look at what a centroid is. A centroid of a cluster of points is the point that is closest to all the points on an average, right? So what's an example here? So let's say you have, this is your, let's say we look at XY plane, or you can say X1, X2. So because then you can actually go to n dimensions. So this is 2 dimensions, right? So let's say you have points here. So which of these points is most likely to be a centroid of this? The one in the center, right? But the centroid, as we're defining here, doesn't have to be a point in the original set of points. It can reflect a center, but it may not be a point that you started out with. So maybe this is a good candidate, but probably the centroid is somewhere here, like bang in the middle. So how do we mathematically define a centroid? That's a question here, right? So we can use a Euclidean distance and say, find the point that's closest to all the points in my given set, and that'll be my centroid. So if we did that, then the centroid is just the average of these points. So take every point. So let's label these points. Say x1, x2, x3, x4, x5, x6. So then I would say the centroid is x1 plus x2 plus x3 plus x4 plus x5 plus x6 divided by 6. Just the average. So why does this make sense? So let's look at also why it makes sense. So the Euclidean distance, I think we haven't covered Euclidean distance yet. We'll be covering it shortly. Okay, so we'll look at why this is a centroid in terms of the Euclidean distance and what that distance is in a bit. But for now, you can just assume, like it makes sense, right? Intuitively, the centroid is like the average of these points. And the centroid is also in the middle of these points. So computing the average gives you the centroid. So maybe based on this, let's look at an in-class exercise. Just take a minute. Feel free to talk to your neighbor and discuss as you look at this in-class exercise. Should be active. And yeah, the other thing I was going to mention is if you don't have the poll available or you're not able to access the poll for any of the in-class exercises we've done so far, just send an email to the grader and we'll kind of take care of it. Okay. Does that sound good? So that you get credit for in-class exercise as well. Okay. So yeah, that was easy. Like just take the average of these points and you get option 4. So we're talking about distance to compute the centroid. So the distance between the Euclidean distance between 2 points is given by so this is called the L2 norm of x1 minus x2. So the L2 norm of some vector is the sum of the square of the elements of the vector, and then you take the square root of it, right? So for instance, if y equals 3, 4, what is L2 norm of y? Five. Yeah. This is 3 squared plus 4. Okay. So the L2 norm is a sense, gives you a sense of magnitude for a vector, right? So basically you're saying, let's look at this 1, 2, 3, 1, 2, 3, 4. So 3, 4 is going to be somewhere here, right? Yeah. So this is 3, 4. So we're basically saying the L2 norm, so let's say this is y, so let's call it y1. So here y1 is in R2, so it's a 2-dimensional vector. So if I place phi on this, it means that the distance is phi. Let's look at a different point. Let's say we have y2 is 2, 1. What is the L2 distance of y2? Square root of 5. So this makes sense, right? It's shorter in length as compared to the other one. So you can say the same thing for the distance between 2 points. So let's look at a different graph. Okay, so we have y1 here, we have y2 here. So the distance between 2 points is basically the L2 norm of the difference. So what's the difference here? The difference vector looks like, so y1 minus y2, right, is this. Does it make sense? So y2 plus y1 minus y2 is y1. So this is y1 minus y2. So this L2 norm of this is going to give you the distance between y1 and y2. What is that? So you just have to compute y1 minus y2 and then compute its Euclidean norm. So what is y1 minus y2? So it's 3 minus 2, which is 1, and then 4 minus 1 is 3. So what is the distance between y1 and y2? So the magnitude of y1 is phi, the magnitude of y2 is square root phi, and the distance between y1 and y2 is square root 10. So the Euclidean norm can be used to compute both magnitude of a vector, but also distance between vectors. Okay. So let's go a little bit deeper and understand why is a centroid the average of the points in a cluster based on the Euclidean distance. Okay. So let's look at the example we had before. So we had these kind of points like this, right? Let's say this is your plane and this is x1. Yeah, I mean, so we'll be switching between x and y, right? So it's okay, x1, x2, x3, x4, xy, and so on. Okay. So we said that the centroid is somewhere in between, somewhere here. Right? So if you want to use the Euclidean distance to compute what the centroid is, you would basically say, let's call this centroid x bar. Okay. So x bar is going to denote our centroid for these points. So based on the Euclidean distance, what would you say? You would say find an x bar such that the Euclidean distance between x bar and xi, let's say squared, and I sum it up over all the I. So let's say here I have 6, 7, 8, 9, 10 points. So find me an x bar such that I am closest to all the points based on the Euclidean distance. Okay. So it turns out this is an optimization problem. All right. So how do you solve an optimization problem? You take the gradient of this function and set it to 0. Or you take the derivative and set it to 0, right? Are you guys familiar with this from calculus? You want to minimize something, some function, you take the gradient or a derivative and set it to 0. So let's call this L of x bar. Why L of x bar? Because x bar is the variable. Everything else is known. You know x1 through x10. You just don't know what the centroid is. So we'll call it x bar. So this is, in machine learning, you would say this is like a loss function. A loss function is something that you want to minimize, right? So here, L of x bar might look something like this. Actually, x bar is in 2 dimensions, right? So it's actually going to be a 3-dimensional loss function, right? Because you're looking at 2 dimensions for the input, and the 3rd dimension is for the value, the loss. So this will be x, the 1st dimension, this is going to be the 2nd dimension, and maybe you'll have a surface like this. So this is going to be L of x bar. So there is going to be some x bar for which this loss function is the smallest. And here we are representing it as a bowl, right? So your bowl-shaped loss function. Like here, your x bar is going to be high. Here, your loss is going to be high, but here it's going to be minimum. So to do that, we'll take the gradient of L with respect to x bar and set it to 0. And that will give you an equation. So here we're saying minimize over all possible values x bar so that I'm closest to all the xi's on an average. To do that, I'm going to take the gradient, set it to 0. So now we need to do some calculus for vectors, right? So it turns out, have you guys looked at vector calculus before for gradients? No? Yes? Maybe? Okay, so we just need one. So for this, we need one main thing, which is, let's say your L of y is the Euclidean norm of y. What is the gradient of L? So we just need to identify this. Once we understand this, we can also understand this and then solve it. So what is L of y? L of y is y1 squared plus y2 squared, and so on, yd squared, where d is the, actually let's not use d, let's use n. N is the number of points in your cluster or in your data set. So what is gradient Lj? It is the partial derivative of L with respect to yj. And what is this? 2y So we're taking it with respect to yj. So we go in here and we see there's only one term in this whole expression that has j in it, which is yj squared. So the derivative of everything else is 0. The only term that has yj is yj squared. Yeah, you guys agree? There's no other term that has it. So this is the same as the derivative of yj squared with respect to yj. So this is 2yj. You guys agree? So for every single j, the derivative is 2y that index. So the gradient is basically going to be the same dimension as your vector. Let's look at. So in this case, we have n. Actually, this is a little bit confusing. Let's actually use yd squared. Okay. So y is a d-dimensional vector. There's d dimensions to it. The gradient is also going to have d dimensions to it. And each dimension, the derivative is 2yj. So that means when we put it together, we get something like this. So the gradient of L here is equal to 2y1, 2y2, so on 2yj, 2yd. You guys agree? So the gradient now is a collection of all these partial derivatives with respect to all the dimensions of the vector. So what is this equal to? If you want to kind of make it concise in terms of y. Remember, y is a vector. 2 times y. Is that right? This is equal to 2y. Why? Because y is actually y1, y2, y3, so on to yn. So this is exactly 2y, where y is actually a d-dimensional vector. So what does that tell us? If you're taking a gradient of a Euclidean norm of a vector, it's just 2 times that vector. So here, I need to take the gradient of the Euclidean norm of a vector, but where you're subtracting some constant vector. So that's the only difference here. So as you can imagine, you can just extrapolate this answer, and you would say it's 2 times x bar minus xi for every single I. Yeah. The constant carries through. So when we do the computation here, you're going to get for every single I. So I have I equals 1 through 10. 2 times x bar minus xi equals 0. So what does this give us for x bar? So you're going to sum over all the I vectors, so x1 through x10, but you're also going to sum over x bar 10 times. This implies 10 times x bar is summation I xi. So this means x bar is summation I xi. So this is how you derive that the centroid of a cluster in Euclidean distance is actually the average of the points in the cluster. So this centroid definition makes complete sense when you say the distance between points is based on the Euclidean distance. Does it make sense? Okay, so that's what we use here. Right. All right, so the notion of distance is very important, so that's why we spend a little bit of time here. So let's move on to cluster distances, right? Or clustering distances. So with respect to clusters, there are 2 main distances that we're going to use: inter-cluster distance and intra-cluster distance. Okay. So inter-cluster distance is a distance between different clusters that you have. So if you have k equals 3, you have 3 clusters. Let's look at the 1 cluster here, the 1 cluster here, and the 1 cluster here. So the inter-cluster distance is basically this. Because it's looking at distance between clusters. And there's many ways to define it. One way to do it is to say intercluster distance is the distance between centroids. within clusters. And maybe you take the maximum or you take the average of it. So typically, a good clustering is going to separate clusters out, right? You don't want clusters to be too close to each other. If clusters are too close to each other, that means they might as well be in the same cluster. So typically, a good clustering would have a larger intercluster distance. So clusters are well separated. And then we have the notion of intra-cluster distance. So in intra-cluster distance, we're saying it's a distance between points within a cluster. So what's the average distance between points within a cluster? And we want this to be small, right? Because we want clusters to be cohesive. Yeah. Like if you have a cluster, let's look at two examples. So we have a cluster that looks like this. And then you have a cluster that looks like this. So both these clusters might have the same number of points, but you see the intra-cluster distance for C1 is larger than the intra-cluster distance from C2, even though they have the same number of points. So this is an example of a good clustering. This may not, because you have, look, maybe you haven't done your clustering right. Maybe it's a function of your data as well. Sometimes you might do the clustering right, but your points are just separated out. And you pick k equals 2, so points that are far away will fall in the same cluster. So it can happen that way as well. But in general, if you want to compare two different clustering options, you would say, try to keep the intra-cluster distance small and try to increase the inter-cluster distance so that the clusters are well separated, but they're also cohesive. So the cohesiveness is coming from here. Right. So this is going to give you cohesive clusters. And this is giving you well separated. So a good clustering is going to have both well separated clusters and also cohesive clusters. So I think we looked at this. Maybe we can do a visual, yeah, why not? So let's say you have something like this. Okay, this is one example. And then let's look at another example. So you have something like this. So which one represents a better clustering? Huh? The first one? Yeah. You guys agree? Can you see it in terms of intercluster and intracluster distance? So what property is different in example 2 as compared to example
1?
Would you need more data?
Well, we need like data points.
Yeah, but visually speaking, sorry?
Intra-cluster distances are just between the points.
Yep. So the intra-cluster distance for this green cluster in the second set of clustering is much larger than expected.
Yeah, more data points.
Let's say they have the same amount of data points. So we are comparing algorithms for clustering for the same data. And let's say they produce these two different kinds of clusters. You can see the third cluster is the same in both the methods, just the first two clusters look different. So here, these clusters are well separated and they're balanced, right? And the intra-cluster distance of any of these clusters is not high. But here, they might be well separated, but the intra-cluster distance for the second cluster is actually very large. Right? So maybe the second cluster has way more points than it should because you can balance it out by moving it to the first cluster. Okay, so let's look at it in class exercise to understand the intercluster distance better. So let's say you apply the clustering algorithm and you got 3 clusters, C1, C2, C3. And we can define the distance between 2 clusters as a Euclidean distance between the centroids of the 2 clusters. So you're asked to compute the distance between clusters C1 and C2. So just apply the definition and see what you get. And feel free to talk to your neighbor. Okay. Okay, so yeah, so we repeat steps 1 and 2 until convergence, right? And kMeans is guaranteed to converge. So you'll not keep oscillating back and forth, like you keep changing centroids all the time. That's not going to happen. After a while, kMeans will converge. So there is, and the reason is you can ask kMeans as an optimization problem, and it's doing some kind of alternating minimization, and that's known to converge. So the math behind kMeans shows that kMeans will not keep oscillating. It will actually converge. But where will it converge? It will converge to some local optimum. So it may not be the best, it may not find the best set of centroids and the best clustering because it depends on the starting point. If you start at a good set of centers, you're going to converge to a good set of clusters that have a good intercluster and intra-cluster distance. But if you start with a bad set of centers, you'll still make improvements, but not as much as if you had started with a good set of centroids to begin with. Okay, so here's an example. So this is, let's say, example 1, example 2. In example 1, kMeans is picking centroids that are sufficiently far away from each other. Okay, and then it's assigning points, recomputing the centroid, assigning points, recomputing the centroid, and then it converges here. Looks well balanced, well separated. That's because your starting points were good. Now let's look at kMeans, where you still pick 3 points randomly as centroids, but it turns out random doesn't mean things get separated out. You might have starting points that are close to each other. So now what happens is your resulting clustering might look like this. So this is not a well separated cluster, right? You can see that this cluster has a large intra-cluster distance. Okay. So the starting point matters for kMeans. All right. Any questions so far? So let's take like maybe a 3-minute restroom break and get some water, and we'll be back.
Okay, no problem. Sorry for
All right.
That should be okay.
So, guys, yeah, let's come back. So far we looked at distance between two clusters or distance within a cluster. Now we'll actually look at comparing two algorithms. So let's say you had two algorithms for clustering. We already saw if you change the distance, the clustering changes. K-means is not good for certain kinds of clusters. So that's why you might want to pick different algorithms, right? So let's say you have the same set of data, but two different algorithms. Here the question is, how do you know which algorithm is better, right? So, and we talked about it. The intercluster distance, the ratio of intercluster distance to intracluster distance, is an indicator for which algorithm might be better. So here, the C's represent clusters coming from one algorithm, and the D's represent the clusters coming from the second algorithm. And you want to look at which algorithm is better, giving you a better clustering. Right? So you want to compare your algorithms. Just kind of go through it and pick a choice. And we can so basically you're looking at this, right? The minimum inter-cluster distance across any clusters given by an algorithm divided by the maximum intra-cluster distance. This is one way to say how good an algorithm is. Again, you can change the minimum to average, maximum to something else. You'll get a different definition for this. But this quantity, you'll get one number for one algorithm. Right? Each algorithm will give you one number for this quantity. So the question is, which one has a lower number? You can also think about intuitively which one should have, like maybe for this problem, you may not even have to do the math. It might be obvious which one has a lower number, but you can still do the math. Okay, so what's your answer? Two? Two? Yeah. I mean, intuitively it makes sense, right? Like, forget about inter-cluster, intra-cluster distance. Just look at the clusters themselves. You'll see C1, C2, C3 are kind of relatively close to each other. Whereas D1, D2, D3, the intra-cluster distance is large, right? So the denominator is going to be large for the D clusters, so which means it's going to have a lower value. So is lower better or worse? Do you want this ratio to be high or low for a good clustering? Low? High? High, right? Because if it's high, that means your intra-cluster distance is small, the clusters are cohesive, and the inter-cluster distance is large, which means they're well separated. So if 2 has a lower ratio, that means it's performing worse in terms of clustering based on this metric as compared to algorithm 1. So algorithm 1 is giving you better clusters. So you want the ratio to actually be high. All right. So this is how you kind of compare two clusterings. Right? Let's move to the issue we had here is if you pick starting points that are too close to each other, you're going to get poor clustering, right? If you pick starting points that are well separated, you're going to get better clustering. And that is exactly what kMeans++ does. It's an improvement on kMeans. So kMeans++ is just adding one more thing to kMeans, which is pick points that are well separated, right? And how do we do that? You pick the first centroid, so U1 is centroid 1, uniformly at random. So kMeans is picking all the centroids uniformly at random. But in kMeans++, you pick the first centroid uniformly at random, like somewhere in there. But for the subsequent clusters, you're going to pick them to be far away from whatever you already picked, right? So you're going to choose it, the probability of picking a point as the new centroid is going to be proportional to the distance between that point and the centroids you already have. So the larger that distance, the higher the probability of picking it. So now it's not a uniform at random probability, it's a probability that's proportional to the distance with what you've already picked. Yeah. And then you keep repeating this process until you have k-centroids. Once you have k-centroids, you can apply k-means. So k-means plus plus is pick centroids smartly to be well separated so that you have good intercluster distance, right? Well separated centroid means good intercluster distance. And then you do k-means on top of that. So let's look at an illustration. Maybe I pick something here. So you shouldn't usually pick corner points as centroids, but let's say my uniform yet random pick this as centroid. Here, I'm going to pick points that are far away from this point as my next centroid. So maybe this is a good candidate. Maybe this is a good candidate. Maybe this is a good candidate. This one is actually going to not be as favorable because the distance is kind of smaller than the distance here, right? I might still pick this because it's proportional, so I'm picking it in a probabilistic way, but I'm more likely to pick these guys as my second centroid. So here, let's say this is my mu1. So my candidates for mu2 could be this, this, or this. So k-means plus plus is then going to say, okay, I pick this, maybe I'll pick this. Now that I pick mu1 here and mu2 here, I'm not going to pick a mu3 here. I'm not going to pick a mu3 here because it's close. So I want points that are well separated from both mu1 and mu2. So I'm then going to probably pick something here. So now I have a mu1 here, mu2 here, and then mu3 here. So this is going to give me good separation. So k-means plus plus is addressing the issue that k-means had, which is the solution depends on your starting point. So pick better starting points. So just a quick summary on k-means. It's a generic clustering algorithm that can take n data points and group them into k clusters based on Euclidean distance. Okay. So the clustering makes sense if the cluster division makes sense based on Euclidean distance. And we saw some clusters that fail this, like spiral clusters. You cannot do clustering for that based on Euclidean distance. Also, let's look at some computational complexity. Yeah, this is something that maybe we should also talk about. So let's say we had 3 clusters. There is n data points. Okay. So now let's say there are, this k clusters, let's say. So here k equals 3, but let's just say k. So roughly you would have n over k data points here, n over k data points here, n over k data points here. Yeah, you agree? Each cluster would have n over k data points. So here k equals 3, so that makes sense. Okay. Let's look at the C step. So C step is computing the new centroid. So let's take a point here. Say it's xi. This is d dimension. So computing the new centroid, I'm going to take the average of all the points in the cluster. Each point is d-dimensional. So I'm going to have a complexity of n over k times d, right? Because I'm taking an average of n over k points in each cluster. So that's n over k times d. But I also have k clusters. So the C step, which is computing the centroid, is order nd, where n is the number of data points and d is the dimension of any given point. And then the other step, where I'm assigning, so the A step, is where I assign points to centroids. So I'm taking each point and saying, do you belong to this centroid or do you belong to that centroid? For every point, I need to do k computations, right? And there are n points, and there is d dimensions. So n, d, k. So this is going to be order n. So if you say, what is the complexity of k-means, what would you say? What is the order? So each step takes order nd plus ndk, but ndk is larger, right? So you'd say it's order NDK. And then how many times kMeans actually goes around, that's usually a constant. So again, that doesn't matter. So the computational complexity of kMeans algorithm is NDK. That's how you would, there might be some constants in there, but it's essentially NDK. Okay. All right. So kMeans plus plus is an improvement on kMeans and yields better quality clusters. Yeah, so both kMeans and kMeans plus plus assume that the clusters are kind of spherical or kind of cohesive in that shape. But if the true cluster shapes look very different, you might have to do something else, like kernel kMeans is one example, or agglomerative clustering. So we might talk about this in the next lecture. If not, we will talk about it in the next course, which is on machine learning next quarter. So if you want to know more about agglomerative clustering, maybe we'll talk about it in the next course, because it kind of deviates from where we're going right now. We're focusing on vision, but in the machine learning course, we're going to look at how to address this issue with not being able to detect spiral clusters. So that's agglomerative clustering. So you can take that course in the next quarter. Okay. So clustering can also be used for data visualization, right? So let's say we had 1,000 images and we wanted to cluster them into a super grid of images, right? So something like this. So each cell here is an image. So there's a super grid of images. Let's say that's what you want to do. And you want to do it in a way that similar images are placed close to each other and not so similar images are far away from each other. So kMeans will not really get us there because kMeans likes a k. You cannot say k equals whatever. So it's not really addressing that issue. So it's not helping us with data visualization. So we want something like this. So if you look at, let's kind of zoom in. This is a bunch of images, but it's a super grid of those images placed in a very particular way, so that images that are similar are close to each other and images that are not similar are far away from each other. So you can see kind of like here, if you look at bottom left, these are flowers, and then you move into fruits, right? And then that moves into noodles, that moves into rice, and then now from rice you've gone into cooking pans. I don't know what else is going on here. Then you go into wheels. So wheels are not connected to cooking pans, but they're circular. So you kind of shifted that, but once you've shifted, you go there. So you keep going this way. It's very interesting. And then you keep shifting and you move into other things. It's a very good set of images. So somewhere in here, you shifted from insects to birds, right? And then from birds, you've shifted to animals, and then animals here, dogs. There's a whole section for dogs in this super grid. There's also people start happening somewhere here. Interesting. It's where you see more of like a vertical object. That's where the transition starts to happen. Where does it happen? Happen here? Here? Okay. So this kind of a super grid, you need a different kind of an algorithm, different kind of method. And one thing that's very popular for data visualization in machine learning is something called stochastic neighborhood embeddings. So in short, tSNE, but you'll also see a more popular version of that, which is tSNE. So T stochastic neighborhood embedding. So tSNE is what it's called. So you can Google tSNE and you'll find a bunch of these kind of images. You can apply tSNE to not just images, you can apply it to other things, like you can apply it to text. You want to arrange text in a particular way, you want to do word clouds, tSNE can be helpful for that as well. So basically for data visualization, not just clustering, it's more than clustering. Right? So in assignment 3 or assignment 2, we'll have a problem on tSNE. So you can apply tSNE and see how it works. So let's understand a little bit more about the stochastic neighborhood embedding and what it does. So the idea is that I might have images, in whatever dimension, like maybe I have an image that's 1000 by 1000 pixels, but I want to kind of identify 2 dimensions to locate the image for the purpose of visualization, right? For instance, here I'm saying, okay, this image is here, this image is here. So I'm able to pinpoint the location of an image. So I want to find coordinates for images so that similar images are close to each other, right? So that's what I'm trying to do. And we don't have a k here, so you can't say pick k equals 3 or 10, right? That doesn't work. So the idea of stochastic neighborhood embedding is to define a probability distribution where, given a point, you can identify the next most probable point. So that way you can actually kind of construct this supergrid. Okay. The advantage of this is also you get an embedding in lower dimension space. So images have a high dimensional embedding, right? Because it's a, let's say 1000 by 1000 pixels, that's in a very high dimension. But with tSNE, you also get an embedding in low dimension. So you not only get to place an image in some point in the grid, you also get to reduce the dimension of that image. So it's also helpful for dimensionality reduction, just like SVD, for instance. Okay. So the probability distribution that's defined here is very intuitive. You just say, what's the probability of picking point J given its point I? I'm at point I, right? So this is, what does this look like? If you've seen some probability before. What kind of distribution does this remind you of? Sorry? Normal distribution, yeah. Normal. Right? You might have seen e to the negative x minus mu square or 2 sigma, something like this. So this is very similar to that. So basically, you say there is a Gaussian that's centered at xi, and you have a distribution over that, and pick the next point j so that I'm close enough to xi in terms of the probability, right? So I don't want to be, so if this is xi minus xj is small, then this negative exponential is going to be large, right? Do you agree? If xi minus xj is very far away, if the distance is very far away, then the negative exponential is going to be small. So the probability decreases. So it's very intuitive. So, but we don't know where the points are for our images. So look at every point that you have, look at every image you have, and see where they are located, and pick whatever it is, x2, x1. So pick the next point that's closest to xi in terms of this distribution, right? So that's how you can sample the points. So basically you're saying pj given I is proportional to the e to the negative xi minus xj squared or 2 sigma I squared. And then there's a second component to the stochastic neighborhood embedding is you get an embedding. So we'll look at this concept of embedding in future classes as well. It's a very useful concept, and it really applies very well to images and videos as well. It's a compact representation of the information that's contained in an image or a video, right? And since it's compact, it has to be low dimension. Your image may be in a very high resolution, so like million pixels, but that's not compact. So it's not enough to locate a point. Like this is for visualization, that's great, but an embedding gives you more concise representation of that image. So here, what tSNE also does is it learns the embedding in a compact dimensional space. For example, yi is low dimension. So it can also be 2-dimensional. If it's 2-dimensional, you can also map it out on a grid, right? You can say this image has this x coordinate and this y coordinate, so put it here. So it's easy to map. But if you look at xi could be an image that has million pixels. So it's not, from xi, I don't know where to put the image in a grid. But from yi, I know how to put the image in a grid. So the yi's give you a representation for the location of an image, or how to put the image in a 2-dimensional space. So essentially, what tSNE is doing is it already knows what the xi's are. So xi's are your images. So this is image I. Yi is a low dimensional embedding of image I. So what the tSNE is doing is it's learning these yi's, a compact representation. And then it's also learning a corresponding probability in the compact dimensional space as well. So given an image I, what's the next most probable j that I can pick to add to the supergrid? Right? And obviously, once you have a probability distribution, you can define a distance between probability distributions. So that's what we have here. KL divergence is like a measure of distance between two probability distributions. And then I can have a loss function. So we looked at a loss function before in the context of a centroid. So almost every machine learning problem has a loss function. So again, you can define a loss function where you're looking at the distance between the original distribution P and the surrogate distribution Q that you're learning and try to minimize it. So you're saying, we'll take these images that are high dimensional, put them in a low dimensional space, but make sure you preserve the distances between them in the process. And that's what this loss function is doing. So you optimize for it. You can do some kind of gradient descent and it'll give you these Ys. That's kind of the gist of what tSNE does. So I think maybe we can stop with this in-class exercise. It's a good idea to see how we can take this tSNE or tSNE and solve this problem, which is going to be part of your assignment. So just kind of brainstorm next 3-4 minutes, and then we'll stop for the day. So maybe kind of pick 1 or 2 people next to you and then kind of break out and discuss this one.